Welcome to After Hours Engineering, Episode 1, Systems on a Chip, or a SoC. This is the first video in a series where we cover and explore the makings of a very simple but functional system on a chip, something maybe along the lines of a ZX81. Because SoCs are a very huge subject, I'm not sure how many episodes there are, nor where we'll draw the line as to how many and where and when they are. But I'll need to draw a line somewhere. So for now, I've decided in this episode we're going to look at VGA and the ECP5, the kind of the setup for the whole series, and go forward from there. So let's go. So we begin looking at the simulation for VGA now. There is a lot of material out there on VGA simulation and synthesis for FPGAs, and so I'm certainly not going to reinvent the wheel for this. I'm just merely going to cover what I did to make it work on the Schoko, which was pretty much nothing. So for the simulation, we have a test bench via Verilator, and it is super trivial. All it does is generate the clock. We have our frequency that we have, run through some formulas to calculate a period, and then we loop through, and every time we hit one clock cycle, if you will, we toggle the clock. This is merely for us to see the timing inside of the test bench as we run it. You don't really need to do this. You could just use the standard clock and just run it. It's just your numbers won't look correctly in the GTK wave output. So I wanted them to look correct so that I could calculate them based on a page that I'm going to show you. Next up would be the top module, where we interface to our hardware, and all that's going to do is the clock. It comes in and we run it into a pixel clock module, which we'll talk about next. We have our horizontal and vertical sync and the counters, and here's the sync generators that also produce a count as well. So here's our pixel clock. All it does is just reflects out the clock that came in and reflects it right back out. Now why am I doing this? Because in the real hardware we're going to actually use a phase lock loop, or a PLL, but I just wanted the code to be structurally the same, so I just routed it in and out of a fake pixel clock. The real meat of the code is this horizontal sync generator, which I pilfered for the most part off of the Alhambra project. And we're going to look at these timing here specs in a minute. So it's really simple code, believe it or not. VGA is relatively simple. You just specify what your resolution is going to be. This is the visible resolution, 640 by 480. And then when you add in all of the front, back porch, and sync amounts, you actually end up with 800 by 525 quote pixels, if you will, or points. The real visible is 640 by 480, but ultimately you're dealing with this many pixels. Set up a bunch of counters, and then I broke the original Alhambra was using all synchronous, but I broke it down into both synchronous and combinational section here. The synchronous part is handling the clock, and we're basically looking to see when we have hit the totals on all of our clock portions here. So remember, even though visually there's 640 pixels on a line, physically there's 525 before you make it to the next line on the display. So we're always looking at the totals and not just the pixels that are visible. Otherwise we would miss the front and the back porch and the sync signal. On the combinational side, here's where we're generating all of the sync signals as they are. Now this could be rewritten as an assign statement for sure, but I just like sometimes seeing it as an if-else statement. And we're checking to see if the display is enabled. Now here's a key point to realize with VGA is that you really don't want to apply color information on the RGB lines while you're in the front, back porch, and the sync pulse. A lot of monitors will just simply not even display an image because they think the signal is improperly formed. One thing you'll really need in your VGA circuit is an enabler which says, hey, these pixels that you're dealing with are actually in the display and not in the back end porches and stuff. So that's what these things do. They check to see, is the counter within the pixel display count? We can see is 640 by 480. That's the visible section. And we're also, you'll see we have a V pixel display. So we're checking to see if we're within that as well. You'll see in the synthesis, where we'll look at this value, and if it's a 1, we can actually apply colors. If it's a 0, we set everything to zeros. And that's it. There's really nothing else to it. There's the display enable, the horizontal sync, and the vertical sync. And again, we're looking at totals as we add everything up and look to see where the counters are relative to display. So this is really nothing more than a counter that's generating horizontal and vertical sync signals. So let's take a look at GTK Wave and see what we got out of this. So here we are looking at the output of the simulation in GTK Wave, and I've set up the timing on the test bench to run 3 frames. Let's take a look at the test bench real quick and scroll down here to the bottom, and I put in enough clocks to at least see 2 to 3 video frames. So let's go back to here. So we can see that we have 3 frames, and each frame is delimited by a vertical sync. So we got 1 here, that's 2, 1, 2, and then 3. Excellent. So the next thing we need to do is take a look at the timing to see if it's correct. Structurally, it appears to be correct. We have our display enable, which is toggling on and off here. It turns off during a vertical pulse, so we can easily see, but when we zoom in, we'll see it turning off quite a lot. So let's go ahead and zoom in. And there you go. You can see that when the display is disabled, we're in our vertical sync, front, back, and porch, and everything right here. So there will be no color information here. But what we really want to look at for now is the horizontal. So let's zoom in and take a look at just this one horizontal sync pulse right here. Now, in order to understand what the numbers are, remember in the test bench, I'll bring that back up here, we set our clock equal to 25 megahertz, and we specifically went out of our way to generate and toggle the clock on every period that we wanted. And I did this for a reason, so that in GTK Wave we get as accurate a clock as we can, show you the GTK Wave signals. So let me bring up another page here, and this page is going to show us the vertical and horizontal sync timing requirements. And I specifically set the test bench to generate clock signals at the right period. So let's take a look at that. This is a typical page out there on the web. There's hundreds of them, but this is the best one I've found that really breaks down the signal. We're going to look on the horizontal side here and the vertical side sync. We're going to look at just a few of those. So let's start with horizontal. We're zoomed in over here. Let's pick B to begin with. So B is the sync signal itself. So we'll put a marker here. We'll use GTK Wave to give us a number up here. So the marker says that we're at 3840. That's the distance between here and here in time. So if we come down here to B, sure enough, we get 3813. Now the numbers aren't exactly the same, but they're really close. And I expect that because I'm rounding off inside of my test bench the numbers. So there's going to be some round off errors, quite a lot actually. We're only off by about 30 something nanoseconds, which every sync monitor can't tell the difference. And again, this is only the simulation. Once we get to synthesis, the clock will be really accurate, and I'll show you how we did that with the PLL. For now, let's take a look at some more signals here. Let's look at A, which is the time between the falling edge of a sync pulse and the next falling edge. So we'll zoom out here a little bit, get to the next falling edge, and we'll move our cursor right here, and we get 32040. So that's A, and sure enough, 31778. We're really close. We're only off by maybe 100 nanoseconds or so. Let's look at the whole sync signal. Now, the vertical sync is going to be a much bigger signal, so that's P, and it'll be rated in milliseconds because it's really large. So we'll need to zoom out on our diagram here. We'll put a marker right there, and we'll scroll over to here, and sure enough, we get 64,000 nanoseconds, which is 0.064 milliseconds. So excellent. Our synthesis is showing that we're right on the money. Now we're ready to take a look at synthesis. So here we are in synthesis, and the first thing we'll take a look at is the make file. So it pretty much looks like all the other make files, except for the list of files that we're actually using. Our Yosis command has changed. The Schoko has an ECP5 on board, so we're going to use the synth ECP5 command instead. We don't need a BLIF file. We never really needed the BLIF file, And we do want to generate a JSON for the downstream processes like the router down here. The ECP5 uses an LPF file instead of a pin constraint file, but it's roughly the same, just structured different. When we compile, we'll do, or build in this case, we'll do a build, a route, a pack, and then we're going to use the Tiger board to upload our bitstream via JTAG. So we do a build. We're still using Yosis. Nothing really has changed there. Then we'll do a route, but this time we're going to use the ECP5 version of the NextPNR router, and we have to change up the parameters to match our board. It's a 45KF ECP5. It has a 256 pin VGA arrangement. We specify our pin constraint file basically, and we're off and go. And then finally we're going to pack it into a bit file using the ECP5 chain. And then finally we're going to use the Tiger board, which uses the OpenFPGA loader. And I did a pull request and updated it to include now the Schoko and the confect. So now we're ready to synthesize. Before we do that, let's check out the top module, simulation to synthesis. The pins have changed a little bit. We certainly are dealing with real outputs on our VGA. We have an RGB LED that you see blinking right now in the display down below there. And you also see we have our VGA that we've routed. So if I was to bring up LPF files and scroll down to VGA, you can see that the VGA pins have all been routed to their pins according to the pin constraint file. And then here's the real thing, and it looks very similar to the simulation, almost identical, except for the lower part has all the fun stuff down below, which we'll talk about real quick and brief. But let's take a look at the pixel clock. Simulation, it was a straight path through. In ours, the pixel clock is using a PIL, or PLL, and we're going to input 48 megahertz, and we want to output a frequency that is commensurate with the VGA monitor. So if we come over here and look at this, we can see that I asked it for an input of 48 megahertz, and I wanted an output of 174.48, which is really dead on to the clock. And it actually gave me that almost identical clock. And now I did have to switch to the high res counter. The low res counter would give me 25.6. which is really on the edge of toleration for VGA. So I did some research, looked up in the PLL manual for the ECP5 and saw that you could pass it the high res command. So it's this property right here that I needed to add in order to get the clock as close as possible to 175. And here I am at 174.8, which is like very accurate. So now we have our clock coming in and our pixel clock coming out and our lock signal. Now let's take a look at some of the fun stuff down here below. We have our red, green, and blue. Now the Schoko board's VGA only has 3 bits of pixels. One for the green, one for the red, and one for the blue, which means we only get 8 colors. But that's okay. The Schoko also has an HDMI connector on it, which gives you full 24-bit color. But we're not there yet. Well, let's just start simple with the VGA. So the first one we're going to look at is, I thought, would be the black background, and I did something simple. And this is where those final 2 signals come into play, the pixel positions. This is really what makes the whole thing work. It's great if you have sync signals and everything, but if you have no idea where you are in the video signal, there's no way you can paint your display. You need to know what pixel you're on so that you can go back to your hardware, so your hardware can go back and scuttle around and figure out what color you need to put at that. Now for our demonstrations, I'm making it really simple. Let's take a look at the black background one. Again, I'm specifically using those positions that are coming in, and I'm taking a look to see, hey, is my current pixel, is the generator giving me a pixel that is within some sort of position, which starts off at 1, and is it less than some 200? Now what this does is it'll form a square on the display, and I did that for each one of the channels, red, green, and blue. So we should see 3 squares, but we'll see one of them is actually moving because I added a little bit of extra fun down here with the counter. I use the 20th bit so the square doesn't move so fast, and I basically count. And when I do, I flip a signal, and depending on which one, I'm either counting up or I'm counting down. So you should see the green one move up and down. That's the green channel. That's why it's a little bit more complicated up here, is because it's checking to see where the green square is. So let's go ahead and launch this. So we'll come down to the terminal down here, and we'll run our make file, and it's going to build it real quick and then upload it, and you'll see it does it real fast. The JTAG is real quick, and there you go. As soon as it updates, and there you are. We have our VGA. You can see the red square, the blue square, and then the green one is bouncing back and forth. That's it. That's all there is to VGA. There's a couple of other tricks you can do. You can turn the background white. So we'll come back to our top module, and we'll enable the white one that we just looked at. Save that. Go ahead and do a make over here. We're making it, and it'll upload it. And there you go. A white signal is now in the background with the same squares as going. Now if we want to see all the colors, I wrote a quick little one here that does a little, it doesn't actually do modulo, but it is interesting. We'll take a look at it. Right here, modulo. It's just basically saying, hey, for every X position range here, we'll set the color value. And again, that color value will be assigned down here to the red, green, and blue channels. So if we go ahead and we've saved that, we'll rerun our make command down there, running it, and as soon as it comes up, there they are. There's all the colors that are capable through the Schoko's VGA port, which is 3 bits. So you got green, red, yellow, blue, cyan, magenta, and white. And then over there to the left next to green is black, but you can't see it because it's black on black. That's it. We've successfully implemented VGA. Nice. The next topic I was going to talk about for this episode was UART, but I've decided to skip it because we've already done UART, and the implementation I did was just an abstraction above that. So I thought I'd dive right into our core CPU for our SoC. And in this case, I've chosen to use the Femto from Bruno Levy. It's a minimalistic RISC-V CPU, and it comes in quite a lot of variants or flavors. The one I'm going to use for our project is the Intermissum version, and I've chosen that because it has the IRQs. It's the first one that introduces IRQs into it, and we will need those in our design, in our SoC. So having said that, let's take a look at what I have. I've barely just started. I have really not a whole lot to show, but we have our SoC. There it is. If I come over to our SoC, we have the input, the ports. That's for displaying LED so we can see what we're doing. A lot of this code has been copied right out of the SoC that comes, the demo SoC that comes with it. And you can see that it's chock full of all kinds of devices for our SoC. SPI RAM, it understands an ICE40, which is the stick that he uses. For us though, I'm extracting just what we need to get the bare minimums up and running. And in this case, the bare minimum is just going to be UART. We'll bring up our SoC, our processor, we'll have it talk to our terminal, and hopefully all of that works. I'm not going to be demonstrating that in this episode. I just wanted to give an overview, a top-level introduction to Femto, the processor that we're going to be using, and what I'm doing. So far I'm integrating in various things like RAM control, our RAM, which is 64 kilobytes, the Femto processor itself, and all of its interfaces, which goes through write mask and strobes and busy signals and interrupt. There's the interrupt flag that we needed. And then my simple stuff that I've added in here for state control, for the simulation only. I just wanted to introduce it real quick. That's what I'm working on in the next several weeks, and maybe I'll have a simulation to show in a few. So we'll see. Let's keep our fingers crossed. There you have it. We've started our next journey, and I'm not sure where the path is going to go, but hopefully we'll get there relatively soon. We'll try not to take an entire year to do a SoC. You never know. At this point, I'm going to continue working on understanding the Femto that we covered just briefly here, as well as maybe some of the various other components on the Schoko. It is possible that in some upcoming episodes there will be non-FPGA specific content, for example the monitor that we'll need to write in order to talk to the Schoko and the SoC that's on it. So, until next time, peace.